Hello friends, welcome back. In today's lecture, I am Dr. Milind Meshram, working as an assistant professor in the Department of Chemistry, CHEM College, Nashik. In the last lecture, we have discussed the Aryl halides. Okay, so we have seen the IPAC nomenclature, and thereafter we have discussed the preparation of various methods for the preparation of Aryl halides. In this lecture, we will discuss the reactions of Aryl halides. Okay. Aryl halides can be react with metal like lithium or magnesium to give the organometallic compounds. For example, Grignard reagent. Alright. Suppose reactions Aryl halide. Suppose when you have this fluorobenzene, when you react with magnesium turning in the presence of CHEM, okay, so it gives phenyl magnesium chloride. Okay, so this is the Grignard reagent. Grignard reagent. This is phenyl magnesium chloride. Alright. So in this way, this phenyl magnesium bromide can be prepared by using this fluorobenzene. When this fluorobenzene reacts with magnesium turning in the presence of ethanol solvent, for example, tetrahydrofuran THF, it gives the Grignard reagent. Aryl halides also react with lithium metal to give the lithiated product. Okay. So generally Aryl halides are less reactive towards the nucleophilic substitution reactions. Aryl halide, for example, fluorobenzene, is comparatively unreactive towards the nucleophilic substitution reaction. But when you apply some drastic condition, for example, higher heating and high pressure, in that case, the nucleophilic substitution reaction can take place. All right. So let us see aromatic nucleophilic substitution reaction of Aryl halides. This fluorobenzene, when it reacts with NaOH 350 degrees Celsius and 300 atmospheric pressure, it gives this phenol. So in this preparation of phenol, this is the precursor. Okay, this is the Dawes process. Okay, so this is Dawes process. So in this process, this fluorobenzene is used as a precursor for the preparation of this phenol. Okay. So similarly, aniline also can be prepared from fluorobenzene. When this fluorobenzene reacts with ammonia, okay, at around 250 degrees Celsius temperature, gives aniline. Okay, along with this ammonium chloride. So this is aniline, this is the phenol. There are also one side product, sodium chloride. Also this bromobenzene reacts with copper cyanide at 250 degrees Celsius in the presence of pyridine, gives benzene, and this cuprous bromide. Okay, so this is the nucleophilic substitution reactions. Generally these reactions inerts. Okay, generally these aryl halides are less reactive or unreactive towards this nucleophilic substitution reaction. But when you apply this kind of reaction conditions, high temperature and high pressure, so this reaction will undergo in this aryl halides. Okay, and when you have this electron withdrawing group, for example nitro group at ortho and para position, so this reaction will undergo easily. And unlike alkyl halides, these aryl halides do not participate in conventional SN2 reactions. Okay, so since SN2 reaction require the backside attack, and this benzene ring is a planar, so that is not possible in this aryl halides. So when you have this electron withdrawing group at ortho and para position, for example electron withdrawing group, for example nitro groups at ortho and para position, so this aromatic nucleophilic substitution reaction will occur. Okay, so let us have this nucleophilic substitution reaction in electron withdrawing group containing aryl halide. For example, aromatic nucleophilic substitution reaction. That is okay. So this reaction aryl halides do not participate in nucleophilic substitution. Nucleophilic substitution reactions. All right. However, when electron withdrawing group at ortho and para positions, then this aromatic nucleophilic substitution reaction would occur. Okay. For example, when you have this is the 1 chloro 4 nitrobenzene. Benzene. When it reacts with NaOH at 170 degrees Celsius in first step, and in second step acid hydrolysis. Okay. So it gives nitrophenol. Alright. So in other case, when you have this two-four nitrobenzene, this is the 1 chloro 2,4 dinitrobenzene. When this 1 chloro 2,4 dinitrobenzene reacts with NaOH at 95 degrees Celsius, the first step followed by hydrolysis, it gives this dinitrophenol. Alright. And when we have this 3 nitro groups 2, 4, 6, 2, 4, 6 nitrobenzene, 1 chloro 2, 4, 6 nitrobenzene, when it reacts with just warm water, it gives this 2, 4, 6 phenol, that is picric acid. 2, 4, 6 nitrophenol, that is picric acid. Alright. Picric acid. So here you can easily recognize the conditions and easily recognize the effect of this electron neutral group, that is nitro group. When we don't have this nitro group at this ortho or para positions, so that aryl halide, that is chlorobenzene, reacts with NaOH at 350 degrees Celsius and along with the high pressure, that is 300 atmospheric pressure. But when you have this nitro group at para position, so this temperature becomes 170 degrees Celsius. When you react with the NaOH at 170 degrees Celsius followed by acid hydrolysis, it gives this nitrophenol. Okay? And when you have this two nitro groups at earth and para, so that temperature becomes 95. So that temperature decreases. Okay. So at less temperature, this reaction undergoes. Okay. When this 2,4-dinitrobenzene, chlorodinitrobenzene reacts with NaOH at 95 degrees Celsius, followed by acid hydrolysis, it gives the corresponding phenol. Okay. And when we have this 2,4,6 trinitrochlorobenzene, it just requires the warm water. Okay. So 3 electron withdrawing groups are present in the aromatic system. So in this reaction, just simply reacts with warm water and gives the corresponding phenol. Okay. 2,4,6 trinitrophenol. It is called picric acid. Why it is so? Because of these 3 strong electron withdrawing groups, that phenolic OH becomes more acidic. Okay. So it is picric acid. Alright. So let us have its mechanism. When this nitro group at ortho position alright, so we have this is 1 chloro 2 nitro benzene. When it reacts with this sodium hydroxide, okay, so in this hydroxyl ion react in this fashion, so this double bond will break. Alright, so it gives so here negative charge will come. Okay. So this is the slow step rate determining step. Okay. So when this hydroxyl ion will attack at this carbon, so this bond get breaks. Okay, and this negative charge come over here. Okay, then in the next resonating form, so this charge will restore over here and this bond will break like this again. This is one more resonating structure, and this So in this way we can show the resonating structures for this aromatic nucleophilic substitution reaction. Okay. So in the first step, this OH ion will react at this carbon, okay, and this bond breaks to form this resonating structure, and then this negative charge will restore and this double bond will breaks, and negative charge will appear come over here, and the second structure, this negative charge will restore and this double bond will get breaks, okay, and this third resonating structure, this charge will restore over here and this chloride ion get depart, okay. So this is the first state. So chloride ion will leave, okay. So in this way we can have our product. Nitrophenol. So you can write this way as well. Nitrophenol. Alright. So you can write this resonating structure like this. Alright. So in this way, this electron withdrawing group, for example, nitro group, plays the important role in this aromatic nucleophilic substitution reactions. So here nitro group present at ortho positions, but when you have these para positions, para positions. Okay. Similarly, this OH ion react. This is slow step, rate determining step. So we will get this resonating structure. In the next structure, this negative charge will restore over here and this bond will get breaks. To get this resonating structure, further this negative charge will restore over here and this double bond will get breaks, and this negative charge will come over here and here Even we can write this like this. Alright. And finally, this is the final step here. Like this chloride ion will depart. Okay. This is the first step. So we can get para-nitrophenol. Para-nitrophenol. Alright. So in this way we can show the effect of this electron withdrawing group, nitro group. Okay. When this nitro group present at ortho and para position, so this aromatic nucleophilic substitution will occur. Okay. So now let us move to other topic. Also, aryl halides also capable of doing the reactions using benzene mechanism. In the presence of sodium amide, this chlorobenzene can be transformed to aniline. Alright. So let us now let us move to other topic. This aryl halide also capable of doing the reaction with benzene mechanism. Okay, by using the benzene mechanism. When aryl halides, for example, chlorobenzene, reacts with sodium amide in the presence of liquid ammonia, it gives the aniline. Alright. So let us have this benzene mechanism. So when this chlorobenzene reacts with sodium amide in the presence of liquid ammonia, it gives aniline. Okay, this is aniline. So this reaction follows the two-step mechanism: elimination and addition. All right. So this mechanism follows two-step mechanism. Elimination and addition. All right. So elimination also a two-step. In step one, is chlorobenzene. Okay, reacts with this amide ion, so it will accept this proton. Okay, it will generate this carbon ion. Okay, in step 2, this elimination of this halide, okay, and this negative charge will restore over here, and this chloride ion will go away. So it will generate this benzene, okay. So in elimination stage, benzene will form, okay. So this elimination reaction is also two-step. So this is the benzene or dehydrobenzene. Benzene or dehydrobenzene. So benzene structure, the additional bond, this is additional bond between these two carbon. All right. Now addition step. This addition is also have the two steps. In the step 1, this benzene reacts with this amide, okay, like this, and this bond will get breaks to form this carbon ion, and next this proton from this ammonia, okay, proton from this ammonia will be attracted by this anion, so to give this aniline, okay. So this addition step is also have two steps, okay. In the first step, this benzene reacts with amide ion to give this carbon ion, and this carbon ion will extract the proton from the acid, in this case liquid ammonia, okay. So this anion will extract the proton from this ammonia to give aniline, okay. So this is how this chlorobenzene is used to generate the corresponding aniline, okay. So it follows the benzene mechanism. Benzene mechanism is of two stages, elimination and addition. Elimination is also have the two steps. In the first step, it will generate this anion. In the second step, this chloride ion will get depart, okay, will get depart to give this benzene. And in the addition stage, this is also have these two steps. In the first step, this benzene reacts with amide ion, and this amide ion get attached to this one of the carbon of the benzene, and this bond get break, and this carbon ion will form, and finally this carbon ion will attract this proton from ammonia to give the aniline. So this is how this benzene mechanism is. So we will see the evidence from benzene mechanism. When you have this chlorobenzene, evidence of benzene mechanism. This chlorobenzene the carbon atom, this carbon is 14 carbon, okay, isotope. So when you have this chlorobenzene, the carbon atom where this halogen is attached, that was means 14 carbon. When you react with amide, this amide ion, okay, so it will give this aniline, corresponding aniline. So two types of product we observed. This aniline. So this gives 47% and this 53%. So almost same. Okay. So in this experiment, so we will be able to say both the carbons are equivalent in this. So in this case, this benzene will form. For example, this benzene will form. This is the isotopic carbon. Okay. So this is the intermediate that can be formed in this reaction. So this amide ion can either attack at this carbon or at this carbon, okay, to give this mixture of product. Okay. So from this experiment, we will be able to say that both the carbons are almost equivalent. From this experiment, this is interpreted by the fact that this label carbon and this adjacent carbons are equivalent, and this NH2 ion can randomly react, okay, to give this mixture of products. All right. So let us have another aspect of this benzene mechanism. Suppose when you have this aryl halide, for example this chlorobenzene, and have the substituent at both these ortho positions, for example 2-bromo, this is the 2-bromo, 3-methyl anisole. Alright. So when you react with the sodium amide, okay, sodium amide, so this reaction will not undergo, no reaction. Why it is so? Because in this anisole there is no presence of ortho hydrogen to this bromo substituent. Okay. So in this there is no presence of ortho hydrogens. That means this benzene will not form. Okay. If that benzene will not form, this reaction will not take place. On the other hand, when you have this ortho and meta bromo anisole, so in both the cases the product will be same. When you have this ortho bromo anisole, so? So let us see this sodium amide, alright, in liquid ammonia. Sodium amide and liquid ammonia gives this carbon ion, okay, this carbon ion, and this meta bromo anisole, it gives two carbon ions, okay. So this amide ion can either affect this proton or this proton. So here we can get two carbon ions. Here, okay, this one carbon ion and this two carbon ion. In this case, now this bromide ion will get depart, okay. So this benzene will form like this. Here also okay, this bromide ion will get this part, and here benzene will form. So in both the cases, this benzene will form. Why it is so? Because this carbon ion is more stable than this carbon ion. This is less stable, okay, because of this inductive effect, okay. So this is the more stable carbon ion. So that means this carbon ion will form, and after forming this carbon ion, when this carbon ion will restore over here and this bromide ion will get depart, so it will generate the benzene, similar benzene, which is formed in this ortho-bromo-anisole case as well, okay. And this amide ion can attack at this carbon so as to generate this more stable carbon ion, okay. So here more stable carbon ion will generate. As we have seen here, the more stable carbon ion. So in this case also, this NH2 negative ion will attack at this carbon so as to generate more stable carbon ion. So this is the more stable carbon ions. And finally, this carbon ion will abstract this proton from this ammonia molecule to get this meta-anisylene, okay, 3 amino anisole, that is called meta-anisotropy. Okay. Now let us move to the other topic, that is reactivity and relative strength of the C halogen bond in alkyl allyl vinyl and aryl halides. Alright. So reactivity and relative strength of C halogen bond in alkyl allyl benzyl phenyl and aryl halide. Alright. So these organic halides contains these C halogen bond. For example, alkyl halide, for example, these primary alkyl halides. Okay. Then there are these secondary alkyl halide and this tertiary alkyl halide. Okay. In this halogen attached to the sp3 hybridized carbon. Okay. So in benzylic as well, this benzyl halide, in this case also this is sp3 hybridized carbon. And then we have this allyl here also this halogen attached to the sp3 carbon atom. But when you have this vinyl, so here this halogen attached to this sp2 hybridized carbon. Similarly, in this aryl halide, this halogen attached to this sp2 hybridized carbon. So as I mentioned it before, these aryl halides, for example chlorobenzene, are less reactive or unreactive towards the nucleophilic substitution reaction. Why it is so? So in this sp2 hybridization, the S character is more, that is around S character around 33%. Okay, 33.33%. So because of that, this bond becomes more stronger than the bond in sp3 hybridized carbon. Okay. For example, this alkyl halides. Okay. So in this sp3, this S character is 25%. So in this case, the bond is bigger than the bond in sp2 hybridized carbon. Okay. So because of that, this nucleophilic substitution reactions is difficult in this aryl halide. Alright. So one more aspect is, so when this aryl halide, for example chlorobenzene, for So this chlorobenzene shows the partial double bond character for this carbon halogen bond. Alright. So when these non-bonding electrons, okay, shows the resonance, so like this. So this bond will show the partial double bond character like this. Alright. So there can be 3 resonating structures here. One more. Here we can show so out of these 4 structures, these 3 are the resonating structures. So here in these 3 structures, this carbon halogen bond shows the partial double bond character. Okay. On the other hand, when this nucleophilic substitution reaction, for example, this allyl halide. So in this case, when this halide will get depart, so we can get this cation. Alright. So this cation can get converted to other cation. This cation can be stabilized by resonance, okay, to form this cation. Similarly, this benzyl halide, okay, so this benzyl cation can also be stabilized by resonance, okay. So here this way. This primary allyl halide and this benzyl halide can undergo the can show the higher reactivity because it undergoes the SN1 reaction, because this initially formed carbocation, allyl cation and this benzyl cation can be stabilized by resonance. Okay, so it will undergo the SN1 reaction. So in this way, this primary allyl halide and benzyl halide can show the higher reactivity undergoes the SN1 reaction. Alright. So this is all about the reactivity and relative strength of the alkyl, allyl, vinyl and this aryl halides. Alright. So this is all about the today's lecture. In the next lecture we will discuss alcohol, phenols and ether. Thank you.